we have now gone through a problem that we have a way of solving analytically. This is just 1D conduction with generation. Generation is constant. Material properties are constant. So we very, very well could have solved this analytically and been done with it. What about a situation where we couldn't solve it analytically, like where something is maybe a little bit more interesting? So let's take an example in the last 10 minutes here where we have properties that are not constant. So here we had these two properties, the electrical resistivity and the thermal conductivity being fixed constant values. In reality, you have this huge temperature swing. If you remember back to the conductivity chart at the beginning of class, conductivity is not constant as a function of temperature. So these, let's assume these are no longer constant, and let's introduce some functions, just whatever we want, but maybe conductivity as a function of temperature is now, say, some linear equation, A plus B times T. And just for simplicity, let's say resistivity is also the same, A plus B times T. We'll call them something else, C and D. C plus D times T. A, B, C, and D are just constants. Okay, so now we have to deal with our set of equations over here. But we have K appearing here, rho E. We have K, rho E here, K, rho E here, right? So now those are no longer just constants, and they're functions. And how do we deal with that? It's not just as simple as swapping out the function. I think there's a little bit of subtlety to it, so it's worth talking through. Okay, so let's kind of go back to our example, and we'll walk through a couple steps just to see where the subtle points lie. So let's start with node 1. Okay, so node 1, and we're going to go through this process of doing the energy balance and writing an equation for it. Again, so let's write out our energy balance. We have Q dot top plus Q dot bottom plus G dot is equal to 0. Right? That's our energy balance. That hasn't changed. It's the same thing. If we write out rate equations for this, I won't derive it again, but we would have K as K now is a function of temperature. So we'll just denote it this way for now. KT times AC times T2 minus T1 divided by delta X plus AC times TH minus T1 over R double prime C plus rho E, which is also a function of temperature, times delta X over 2AC I squared equals 0. Right, that is the same thing we had before, but we've now noted that there is a function of temperature. So the real question is, what is the temperature that I'm using to evaluate these properties? This is really the only tricky part to this. Right, so here I need to figure out what is the temperature I'm using to evaluate. Well, okay, the first inclination would be, let's say KT is K at T1. Don't do that, that's wrong. Okay, why is that wrong? And this is the subtle point. So if I'm sitting here at node 2, and I look up to node 1, and I see that there's this heat flow coming in from node 1. What is the rate equation I use to calculate that? Right, it's the same rate equation that I'm using if I'm sitting at node 1 looking down to node 2. So those two things, the heat flow from whatever perspective you're starting from, that heat flow crossing that boundary has to be the same. Right? If it's not the same, I'm creating energy or destroying energy at that boundary. We obviously can't do that. It violates the laws of physics. So we don't want to do that. So we need to figure out, okay, I need to evaluate that conductivity at a temperature, a mutually agreeable temperature, so that both those heat flows going in both directions are the same thing, differing only by the sign of the heat flow. Okay, so knowing that, we want to then evaluate conductivity, K, at the average temperature between those two nodes, or the temperature at the boundary. So that would just be T1 plus T2 over 2. All right? That's where we're evaluating our conductivity. Incidentally, this is relevant for your homework. That goes for area as well. So you always have to make sure when you're formulating the numerical equations that the heat flow between two nodes aligns, no matter which way you're evaluating that same equation. So if the area was changing, you would evaluate the area at that boundary instead of the area at the center point of the node. Okay, so here, this is where, right, we add this in. This is our function. We now evaluate conductivity at that point. What about rho E? Does rho E need to be evaluated at the average temperature? Think about that for a second. The answer is no, it does not. And why is that? Because rho E is a generation associated with that control volume. Rho E is not have to be agreed upon by adjacent nodes. It is just for that one node. So for rho E, we can evaluate that. We can say rho E is just at T1. Okay, and we do that and we're happy. So same thing, same approach applies for nodes I, where you're doing the average at Ti minus 1 plus Ti, or the average at Ti plus Ti plus 1, if that makes sense, right? So you're always doing the same thing. We just have to be careful. We're evaluating it at the boundary in order to get the heat flows to agree. Oops, why is it? There we go. Okay. Yeah, any questions on that? No? Okay, so then let's just look really quickly at how we implement this. Last thing we'll do today. So let's implement this in, well, okay, so first I'll say in ease, it's really easy, right? You plug it in, you're implementing it in ease, you just put in the temperatures, it'll solve everything simultaneously and you're happy, right? So there's really no trick to it there. The part where it's maybe a little bit more tricky is in Matlab. So first what we have to do in Matlab is we're gonna, for every function that we have, you make a standalone file. I think that's kind of the way Matlab has to work. So you make a standalone file, you put the function in there. So the function is gonna be, here's the name of my, here's the thing it's returning in brackets. We're returning conductivity K, so that thing has to be assigned somewhere in the function. And then this is the name of my function, Kf. And it takes as an argument T. All right, so K is equal to then, here's my linear function for conductivity. Same thing for resistivity, right? It's calculating and returning rho E, and it's taking temperature as an argument. So these all live in the same folder as your main solution. Okay, so here's now the same solution we had before. Right? This is this one over here, our matrix inversion example, but now we're doing it for temperature dependent properties. Okay, everything's the same up until the point where we are assigning the coefficients. So here, A11, now we have, instead of just plain old minus K, we have this function. Right, so this is the function that we're evaluating. So we evaluated at our guess temperature divided by 2, the average temperature, and then that's what we're using, right? Same thing for resistivity, but just at the one temperature. Okay, so you go through that process, solve it the same way, and hopefully it solves, right? And we can get an answer. Oh, I guess I don't have a plot here, but okay, so it solved. We converged, everything was fine. You can do the same thing for Gauss-Seidel. I wish I had like 2 more minutes, but we'll leave it here. In Gauss-Seidel, you do the same thing, but now the important point is you need to evaluate the properties. This is a critical thing. So you have to evaluate the properties at existing temperatures that you have already guessed, right? Because you can't evaluate properties using temperatures you haven't guessed yet. So first guess the temperatures, evaluate the properties, plug that in, and you can have this solution that way. Okay. We'll recap that a little in the next lecture. All right, thanks everyone.